Round-off error. A round-off error, also called rounding error, is the difference between the result produced by a given algorithm using exact arithmetic and the result produced by the same algorithm using finite precision, rounded arithmetic. Rounding errors are due to inexactness in the representation of real numbers and the arithmetic operations done with them. This is a form of quantization error. When using approximation equations or algorithms, especially when using finitely many digits to represent real numbers, which in theory have infinitely many digits, one of the goals of numerical analysis is to estimate computation errors. Computation errors, also called numerical errors, include both truncation errors and roundoff errors. When a sequence of calculations with an input involving any roundoff error are made, errors may accumulate, sometimes dominating the calculation. In ill-conditioned problems, significant error may accumulate. In short, there are two major facets of roundoff errors involved in numerical calculations. Digital computers have magnitude and precision limits on their ability to represent numbers. Certain numerical manipulations are highly sensitive to roundoff errors. This can result from both mathematical considerations as well as from the way in which computers perform arithmetic operations. Representation error. The error introduced by attempting to represent a number using a finite string of digits is a form of roundoff error called representation error. Here are some examples of representation error in decimal representations. Increasing the number of digits allowed in a representation reduces the magnitude of possible roundoff errors, but any representation limited to finitely many digits will still cause some degree of roundoff error for uncountably many real numbers. Additional digits used for intermediary steps of a calculation are known as guard digits. Rounding multiple times can cause error to accumulate. For example, if 9,945,309 is rounded to two decimal places 9.95, then rounded again to one decimal place 10.0, the total error is 0.54691. Rounding 9,945,309 to one decimal place 9.9 in a single step introduces less error 0.45309. Floating point number system. Compared with the fixed point number system, the floating point number system is more efficient in representing real numbers, so it is widely used in modern computers. While the real numbers are backslash display style backslash math are have are have are this is bar bar r have r it is bar it is bar are infinite and continuous, a floating point number system. F backslash display style f is finite and discrete. Thus, representation error, which leads to roundoff error, occurs under the floating point number system. Notation of floating point number system. Normalized floating number system. E standard. In the E standard, the base is binary, i.e. B equals 2 backslash display style backslash beta equals 2, and normalization is used. The E standard stores the sign, exponent, and mantisse in separate fields of a floating point word, each of which has a fixed width number of bits. The two most commonly used levels of precision for floating point numbers are single precision and double precision. Machine epsilon. Roundoff error under different rounding rules. Calculating roundoff error in E standard. Measuring roundoff error by using machine epsilon. Theorem. Proof. Roundoff error caused by floating point arithmetic. Even if some numbers can be represented exactly by floating point numbers and such numbers are called machine numbers, Performing floating-point arithmetic may lead to round-off error in the final result. Addition, multiplication, division, subtractive cancellation, accumulation of round-off error. Errors can be magnified or accumulated when a sequence of calculations is applied on an initial input with round-off error due to inexact representation. Unstable algorithms. Ill-conditioned problems. Real-world example: Patriot missile failure due to magnification of round-off error.